My talk today will be about tree tensor networks or tree-based tensor formats that we have seen in several talks this week. But in a learning setting, I will try to give you some old and recent results on what we can expect from this tensor of approximation formats in a learning setting. So there are a few results in collaboration with Erwan Grelier and Bertrand Michel on the learning part, and some results I will give you on approximation part that we have obtained with Marcus Barmaya and Reynold Schneider. So what are the typical tasks in learning? First, the approximation of a random variable y as a function of a set of random variable x, x1 to xd, from samples of the pair x and y. This is a classical framework of supervised learning. The other typical task is the estimation of a probability distribution of a random vector from samples of the distribution. This is the typical task of unsupervised learning. So I would like to give you a framework for using tree tensor networks within these two settings. The framework we will use here is empirical risk minimization. So the first thing to do is to introduce a risk functional, which is such that the difference between RV and RU give you some measure, some distance between the approximation V and the target function U, called also sometimes the oracle. And then you will define a risk functional as an expectation of some contrast function. So what are the typical examples? In a supervised learning setting, let me give you the example of least square regression, where the risk functional is defined as the expectation of the square of the distance between y, the random variable you want to approximate, and the prediction you obtain through your function v. Okay? This is a typical L2 distance between y and the prediction. Here in this context, the oracle is the conditional expectation of y given x, and the difference between R and v and R and U, the oracle, is no more than the distance, L2 distance to the square between U and V. Okay? L2, weighted L2 distance, where the weight is the probability distribution of the variable x. In unsupervised learning, you can have many choices of contrast. The simple choice is a L2 loss, where you choose this contrast function here, takes the expectation, and you define a risk such that the difference between RV and RU is again the square of the L2 distance between U and V, where here the oracle is the density of the probability distribution with respect to some reference measure, okay, which could be Lebesgue or other measures. Okay, so these are two typical settings where you will work in L2, okay, and this most of the results I will give you from the approximation part will be in this L2 setting. Well, now coming to the practice, what we do. What we have is a collection of samples of the random variable z, and then an approximation is in practice obtained by minimizing an estimation of the risk, which is no more than the statistical estimation of the risk, given the samples. And this minimization is performed over a certain model class, okay, of moderate complexity. If you denote by UF the minimizer of the true risk over the class F, usually we split the error into two parts, an estimation part, which gives you the difference between the risk associated with the approximation you have constructed by minimizing this, and the risk associated to the best you can expect from your model class. The second part is the approximation error, okay, which is the difference between the risk associated with the target and the risk associated with the best you can expect from your model class by minimizing the risk. Okay. So it is well known that if you consider larger and larger model classes, then the approximation error will decrease, but you will have an increase of the estimation error. So the methods that we would like to propose have to balance these two errors in some way, and in order to take the best from the available information. Well, so the talk will be split into three parts. First, I will briefly recall you what are these tree-based tensor format or tree tensor networks. Then I will give you some more or less standard, and some new results on estimation errors and approximation errors using these approximation formats. And in the third part, I will briefly give you some, I will present heuristic algorithms on how to do, in practice, empirical risk minimization and adaptivity within this format, which is a crucial practical part. Okay. So first, tree-based tensor format. So the setting is the following. I will consider a space H of functions defined on a product set, equipped with a product measure. Then for a subset of variables in 1D, you can identify a multivariate function with a bivariate function, a function of two groups of variables, variable x alpha that collect all variable xi, I in the collection alpha, and the complementary set of variables. And then we will define a notion of rank called the alpha rank, which is the minimal integer R alpha, such that you can express your multivariate function as a sum of R alpha product of functions of groups of variables. Okay? So this minimal integer, such that V can be represented like this, is called the alpha rank of the function. Now, by introducing T, a collection of subsets of variables, you can introduce a tensor format, this set of functions, such that the alpha rank is bounded by some integer for any alpha in this collection of groups of variables you have chosen. Okay? This is called the tensor format. And in the particular case where T, the collection of groups of variables you choose, is structured as a tree, as a dimension tree, we call the format a tree tensor format, a tree-based tensor format, or tree tensor networks. The word tree tensor networks can be seen from the following slide here. When T is a tree, you have a very nice property that elements of the tensor format have an explicit representation in terms of low-order tensors. So let me precise this. Consider H a tensor space. This is the background approximation space where the functions live. Consider function in L2 and introduce basis functions, univariate basis function for any space H nu. Typically, consider polynomial, wavelets, or any approximation, a standard approximation tool. Then a function in this tensor format will have an expression like this, as a multiple sum of products of components of low-order tensors, A alpha. Each of these tensors, A alpha, are associated with a node of the tree. Okay? And this is why we call this approximation format tensor networks, because they are parameterized by a collection of tensors organized in a tree. Okay? The representation complexity of such a function here can be written like this, and is a function of the ranks you have imposed and the dimension of the background approximation spaces. Okay, now there is another interpretation of this approximation format as neural networks. And for doing this, you can identify the low-order tensors associated with each node with a multilinear function, which is a vector-valued multilinear function. In fact, these functions are associated with the different nodes. They will take as inputs a vector coming from the sons, and there will be, as an output, a vector also. Okay? Any tensor can be identified with such a multilinear function. Okay? If you do this, you can write your tensor format, an element of your tensor format, as a composition of multilinear functions. Okay? Written like this. And, okay, sorry, here's this notation, phi1, phi2, etc. are called in a learning setting the feature maps. They are associated with the basis function you have chosen for the spaces of univariate functions. And this can be interpreted, in fact, as a deep networks with a sparse architecture given by the tree, a depth which is bounded by the number of variables because of the very particular format. You have a depth which will be bounded by d minus 1. And the width at a given level is related to the alpha ranks you have imposed for the node in this level. Okay? So this is a known architecture, but here within with this particular choice, you have many favorable properties, and most of them I will recall them in the next part on estimation and approximation error. We have many things to say about this particular format. Here I will start with some very standard result in estimation error. The new thing will be the complexity analysis of these three tensor networks, but let me start with a very standard analysis for obtaining bounds of the estimation error. Given a model class F, a minimizer UF of the true risk over the model class F, and a minimizer U hat NF of the empirical risk over F, then the estimation can be easily bounded by a sum of two terms that takes the difference between the true risk and the empirical risk for functions here that are in the model class. From this, you can obtain different types of results in probability, in expectation. To make it simple, I will only give you results in expectation. Well, I try to bound the average of this error. Okay, the average over the samples of the difference between the risk of the estimation and the risk of the best approximation in the model class. Because the empirical risk is an unbiased estimation of the risk, when you take the expectation, this cancels. It remains only this term. And you can obtain very easily a bound of this term by taking the expectation of the supremum over all the model class of the difference between the empirical risk and the risk. Okay? This has been seen in a talk already yesterday. The empirical risk is an average over the samples of some random variables associated with the contrast you have chosen and the expectation of this contrast. So to obtain, in fact, bounds of the risk, the idea will be to use some concentration inequalities. Okay? Yeah? Subscript where? Here? Yeah? What is UF? The hat here? It's just to mention that it is a statistical estimation. Yes, because, okay, there was one step missing. In fact, you use the fact that U hat NF is a minimizer of the empirical risk. So you have three terms, but one is bounded by zero. Okay. In fact, you have plus this term, minus this term, but this additional term is less than zero, because you suppose that the U hat is a minimizer of the empirical risk, and I will come back to this later. Okay, so now standard assumption in order to obtain a bound of the estimation error is to assume that the model class is compact in L infinite, and I will further assume that for any functions in the model class, I have a uniform bound of the contrast, and also a Lipschitz continuity of the contrast, uniform Lipschitz continuity with respect to the first argument. So these are standard hypotheses that are satisfied in the L2 settings that I have mentioned before. And then you have many ways to obtain bounds. A very standard concentration inequality, like Hoeffding, allows you to obtain a bound of the probability that this empirical mean deviates from the expectation by more than a certain epsilon m. Okay? And this bound is exponential with respect to the number of samples, n. Okay? Having this and using the compactness of F and the Lipschitz continuity of the contrast, you obtain a uniform bound on the probability like this, where here the supremum over F is inside the probability, as you see. And here you will lose a factor, which is the covering number of the set F. Okay? At a scale that depends on the bound M, on the Lipschitz continuity L. These are standard results. And finally, you obtain very easily a bound on the expectation of the error by epsilon m plus 2m times the probability that you have here. That depends on n, on epsilon, and the model class you have. Okay? And then a bound can be obtained by taking the infimum over all epsilon that you have here. Okay, now, nothing specific to tree-based format, so what we need, just to obtain a bound, is to have an ID of the covering number, or equivalently, the metric entropy of the tree-based formats. So here I will assume that my background approximation space H is in L infinity, with basis function normalized in L infinite. For any representation of V with the parameters F alpha I had introduced before, the multilinearity of the format, in fact, the representation is linear in each of the F alpha. So you have, very easily, this inequality. That means that the norm of V in L infinite is bounded by the product of the norms of F alpha. And here you have a flexibility on the choice of the norms, and I define the norms such that the constant here is 1, okay? You obtain it with this particular definition of norms. I don't go into the details. It's related to injective norms of tensors. And then the model class is defined as a scaling of this set F1 where all the functions have a norm bounded by 1. And if you do it like this, you can show quite easily that the metric entropy, the log of the covering number, is bounded by a logarithm of the scale tau minus 1, or the radius of this model class, and times here the representation complexity. So in fact, the metric entropy here behaves as a linear approximation space for these three tensor networks. Okay? You have a metric entropy which is proportional to the representation complexity of elements of the model class. Having this, you will obtain a bound of the estimation error like this, under the condition that the number of samples is greater than this expression, which is linear in the complexity of the representation, logarithmic in the inverse of the probability you have here, and then when you take the infimum over epsilon, as I said before, you obtain a bound, which is a typical bound, as a square root of the complexity of the format divided by n. Okay, so it's 1 over square root of n, and it's proportional to the square root of the complexity. The same type of bounds you obtain, at least using Hoeffding inequality, for linear approximation spaces. Okay? Here it's a nonlinear approximation format, but here it behaves like linear approximation format. Okay, now coming to the approximation part, we would like to have an idea of the approximation error, which is a minimum over the model class of the difference between the risk RV and the risk associated with the target functions. We would like to have an estimation of this error for a given function class, at least consider the standard function classes. And in some other words, it's called the analysis of the expressive power of the three tensor networks for particular function classes. Well, so here I will restrict I will give you some results in the particular L2 setting, where we are able to obtain bounds using some known tricks in tensor calculus. In this L2 setting, the best approximation error is the minimum of the square of the L2 distance between U and V. I will denote this best approximation error by ETR. T is a tree, R is a tuple of ranks. Since the tensor format is in fact an intersection of spaces, each space here is a space of functions where you just impose one of the alpha ranks. Okay? When you take the intersection of these function spaces, you obtain your tensor formats. Then it is really straightforward that you have that the best approximation error as a lower bound, which is the maximum of all best approximation error by elements with just one of the alpha ranks bounded. Okay? So, first, before going to the upper bound, let's try to give some information on this. For that, there is a very standard tool, which is singular value decomposition. A multivariate function in L2 can be identified with a bivariate function of two groups of variables, in L2 of a product of two sets. These are denoted X alpha. Alpha is a collection of variables here. And in this Hilbert setting, you have the existence of a singular value decomposition of this bivariate function. The sigma k alpha has a singular value decomposition of this bivariate function and are called the alpha singular values of the initial multivariate functions. Of course, you have as many singular value decomposition as the number of choices of the collection of variables alpha. Okay? For any group of variable alpha, you can have a different singular value decomposition. Okay? Now it is well known that the best approximation error by elements of alpha rank bounded by R alpha is obtained by truncating this singular value decomposition at the rank R alpha. And the best approximation error that we had here, this best approximation error that you see here, is a function of the singular values you have rejected, okay? You have truncated here this decomposition, and the other singular values appears in this expression of the error. Well, there is another way of writing this best approximation error. If you consider the space U alpha generated by these functions here, that are called the principal components associated with a group of variable alpha, you have this expression of the best approximation error, which is a minimum over all subspaces of dimension R alpha of the integral of the difference to the square between partial evaluation of U minus the projection of this partial evaluation on the subspace U alpha. And the subspace of principal components is a solution of this optimization problem over all subspaces of dimension R alpha. Now, this is the way principal component analysis is written down usually. Okay? Now, if you introduce this set, K alpha U, of partial evaluations of U, so I take the partial evaluation of my multivariate function for a particular value of this collection of variable X alpha complementary, this will be a subset of L2 defined on the product set X alpha. If you assume that mu is finite, you obtain easily a bound here by taking the supremum of this over the set that you have here. You obtain that this best approximation error is bounded by the minimum over all subspaces of dimension R alpha of the worst error of projection on the set K alpha, which is no more than the Kolmogorov width of the set which is here. Okay? So there will be essentially two ways of obtaining bounds for this approximation in tensor formats, either using results on singular value decomposition or bilinear approximations. This was done by Reinhold Schneider and Andrei Ushmajev, for example, several years ago, or using some knowledge about the Kolmogorov width of this set. Okay? This will be two ways of analyzing errors. There is something to note here. Since the best approximation error E alpha R alpha is the same as E alpha complementary R alpha, because essentially the alpha ranks and alpha complementary ranks are the same, you obtain a sharper bound, which is a minimum of the Kolmogorov width of two types of partial evaluation. Either you evaluate partially with variable X alpha or X alpha complementary. Okay? Well, so now how to obtain an upper bound? So this is maybe a coarse way to obtain it, but something we have with the tool in this tensor calculus. Given the principal component spaces U alpha, for any alpha in your tree, you can define an approximation by successive orthogonal projection in these subspaces, ordered in a suitable way. This is related to higher order singular value decomposition. And with this particular approximation, you obtain a bound. The square of the error with this particular approximation is bounded by the sum of the square of the best approximation errors we have seen previously, where you impose just a rank for a particular group of variables. Okay? And of course, because this element is an element of your of your model class, this is an upper bound of the square of the best approximation error in your model class. Okay, so this is the way you obtain an upper bound, and then you can use either results on singular value decomposition or Kolmogorov width of these sets to obtain a bound of this. Okay, so let me now give you some examples. So for standard regularity classes, there have been results have been obtained by Reynolds Schneider and Reusch-Majeff, and recently also for other classes by Griebel and Archbrecht, that show that in fact that they perform not as optimal approximation tool, but almost in an optimal way. Let me give you a particular example for mixed Sobolev spaces. Suppose that U is in a mixed Sobolev space, HK mix, defined on the IP cube here. Then you can use either singular value decomposition or the trick with Kolmogorov width. Here I will use the trick on Kolmogorov width. The partial evaluation for HK mix will also be in HK mix space. So then, knowing the behavior of Kolmogorov width of Sobolev both, you can have a bound on the complexity to achieve a certain precision epsilon, which will be like this. Here you see that compared to standard approximation tool like hyperbolic cross approximation, you lose some powers here. But essentially, you don't see the dimension in this term. You see it here with the log of the epsilon minus 1, which is the standard thing you obtain with standard hyperbolic cross approximation tools. But, okay, so here, of course, we cannot beat the curse of dimensionality with these formats, contrary to what we can see in the literature. It's not because the number of parameters is linear in the dimension that we beat the curse. There is an oracle that we cannot beat, but we are not too far from it, okay? But, of course, imposing more structure, not standard regularity assumption on the functions, we can obtain better results. And in particular, we have obtained with Marquis-Barr-MAIA and Reynolds Schneider some results on a family of functions that are composition of regular functions. So if you consider such function class, where all the functions here are smooth in this way, in fact you consider this function in Sobolev spaces WK infinite, with L infinite norm bounded by 1 and these norms, WK infinite bounded by B, then, after some work, and using the tricks I have shown before, using Kolmogorov width of these multivariate functions, you obtain a complexity bound, which is like this. So you don't see the dimension anywhere except in the L. What is the L? It is the number of layers in your tree, okay? The depth of your tree, which will be for balanced tree a logarithm of D, or which will be linear in D if you use linear trees. But here you see that you have the curse of dimensionality through the B, which is the norm of your function here, okay? So composing again and again functions with some high norms in their derivative, you pay the price, okay? Not too bad for balanced tree because you are logarithmic in D, but when D grows, okay, you will pay. So bad influence of the depth for functions with high norms. Just a particular comment here. In fact, working a little bit harder, you can prove that this power of L only appears on the norm of the first derivatives, not the other ones. Which means that if you have one Lipschitz functions, b less than 1, or even one Lipschitz functions, the complexity only scales polynomially in D, because this term disappears here, okay? So you have no curse of dimensionality, but in the case where you limit the complexity of the function you compose, okay? Okay, so now a few words about, yeah?
So we have not introduced this composition structure. This was the idea of Mascard and Bocci.
Yeah, of course, it's particular model class. Yeah, I should say that if you want similar results for neural networks, these functions have been considered to analyze the expressive power of neural networks for this particular class of function. Yeah, it's Mascard and Poggio recently. But in fact, I would say, given the expression of neural networks and tree-based formats, it's very natural this type of function is really related to the format you use, okay? And this is why it works. And here the choice of tree is crucial, and I will come to this soon. If you don't have the structure of the function like this, you will pay it, you will see. So a first word between, is it good to use tree-based format compared to canonical format? Canonical format was discussed by Wolfgang Dahmen in a previous talk. There are some nice results for some function classes for this, but there are also bad results, I would say. So first thing to note is that any function in a canonical format like this, which is a sum of product of univariate function, can be encoded with a slightly higher complexity in these tree-based formats. Okay, you will lose a little bit. If you have a function written like this, you will pay a little bit more by written it in a tree-based format. But conversely, if you have a typical format in a tree-based format, a typical function in this format, you can show that it has a canonical rank depending exponentially in D for a typical function in this set. These are results obtained by, in a sequence of papers, particular Cohen, and then a paper with Kulkov and Ozoledets. So, which says essentially that deep is better typically for typical functions. Okay, considering tree-based formats will be beneficial. But also a comment here that a typical function in some tree-based format may have a representation which has a complexity exponential in D in another tree-based format with a different tree. And I would like to give you an example here. Consider the probability distribution of a Markov chain, which is a product of bivariate functions like this. And suppose that the bivariate function you see here have a rank bounded by R. If you choose a linear tree containing as interior nodes 1, 2, 1, 2, 3, 1, 2, 3, 4, and so on, which is which leads to the classical tensor train format, then you can prove that the complexity of the representation of F in tree-based format will be in R to the power 4, okay? But now, okay, something also, you can show that the canonical rank for this representation will be exponential in D. So here, it's beneficial to go to tree-based format. But also, suppose that you have no idea about the causality of your system. You have no idea about the sequence of variables, how they are dependent with respect to each other. And suppose you have chosen a tree, which is a linear tree, but with variables ordered like this, okay? And this is the worst case, in fact, where you can prove that the representation complexity of F will be exponential in D also. So you have a problem of finding a good tree for a particular function, and this part is really complicated. It's a combinatorial problem, okay? But this will be part of the problem. If you want a black box algorithm, that try to approximate a function for which you don't know anything, about the structure of the function, you will have also to play with the tree if you want really to obtain good performances of your algorithms. So now I have some time to describe you learning algorithm, because the result, combining the approximation results you have seen with the estimation, with result on estimation errors, you can obtain standard results about the global error, okay, you obtain. It's different of the risk associated with your estimation and the ideal risk, okay? But all the analysis that I have done before is based on the assumption that I am able to obtain a minimizer of the empirical risk. The model class here is a nonlinear set, and as neural networks, we have this issue also of solving the optimization problem, how to minimize the empirical risk over these model classes. So I will give you here, I will present you some algorithms. So it's a complicated problem, nonlinear approximation problem, but the structure of the model class is such that the algorithm will be quite simple to derive. As I said before, we have a multilinear representation of the format. Any function v of x can be written as a multilinear application of the different tensors A alpha of your parameterization. Okay? And because this map is multilinear, linear in each of the alpha, then the partial maps that you see here that associate to A alpha the value of V of X is linear, okay? I will write this partial map in this way. Because A alpha is a tensor, you can identify this linear map here with the inner product of A alpha with a tensor, C alpha of X. Okay? So now when you go to the minimization of the empirical risk, which is the average of the contrast, depending on the different samples you have, you can use very natural alternating minimization algorithm. You will minimize successively on the different parameters. When you optimize on a particular A alpha, you will obtain an empirical risk minimization problem over a linear model class. Okay? When you optimize only on a single parameter A alpha. This is a linear approximation problem that you have here. And for this, you can use standard optimization tools that have been derived in this learning setting. Also, you can use standard tools to exploit the sparsity also in the representation in your tensor format. The different tensors A alpha may be sparse for some function classes, so you can exploit this in different way. The way we do it here in practice is to consider sequences of spaces, so it's kind of working set strategy. We consider increasing sequence of spaces at the leaf of your tree, and consider different approximation of increasing complexities, and we use standard model selection techniques. Here, in the example I will show, it's based on cross-validation, so it's a validation technique to select the model. You can have also other techniques based on the regularization of this empirical risk minimization techniques and so on. But this is quite standard because here at each step, the model class is linear. For fixed parameter A beta, beta different from alpha. Well, also a particular, I would say an important point in this L2 setting and using this format is that you can obtain quite robust and stable algorithms. Any function in this format that means many equivalent representation. You see this multilinearity of the format is such that you can rescale your different parameters A alpha in such a way that you don't change the function V you represent, okay? And there is a way to change the representation of a function such that you can write for a particular alpha, the function V of X, as a sum of functions ck alpha times the entries of the tensor A alpha with the function here that are orthonormal in L2. Okay, there is a way. It uses standard linear algebra tool, QR factorization of matricization of the tensors and so on. But the thing is that at each step of your alternating minimization algorithm, you have a linear approximation format with basis functions here that are orthonormal in L2. And it gives you many favorable properties from a numerical point of view, of course, but also from a statistical point of view. Okay, now there is a problem. A model class is determined by the tree and the ranks. And choosing the ranks, this tuple of ranks, you have D integers, O of D integers to choose, so it's a complicated problem if you have a black box function to determine this rank. So you need an adaptive procedure in order to adapt the ranks. So here we propose a heuristic strategy. So I think that behind this we could obtain some results. We have some early results about the quasi-optimality of this type of procedure, but we need many assumptions. So let me describe you briefly these heuristics here. The idea is to build a sequence of approximation with increasing ranks. The strategy will be easy. At each step, we will enrich the rank for a particular selection of nodes in your tree, okay? So this set Tm, theta, will be the set of ranks you will increase at each step of your algorithm. So what are the nodes to choose at a given step? If you have an idea about the best approximation error with functions with the alpha rank bounded by the current rank you have an idea of how bad it is to truncate this alpha rank, okay? If this error is high, that means that you have a potential gain in increasing this particular rank associated with alpha. So the strategy will be to select all the nodes such that the truncation error is greater than a certain factor than the worst error, the worst truncation error, okay? It's kind of bulk search strategy here. That maybe you recognize the way you can define a bulk search strategy in adaptive approximation. If theta is equal to 0, you will retain all the nodes, so you will increase all the rank. It's an isotropic enrichment of the nodes, not very interesting. If theta equal to 1, usually you will only enrich the rank associated with a single node, okay? The algorithm will be quite slow in this way. For least square regression, we have tools in order to estimate the errors, because the difference of the risk is the square of the L2 distance. The truncation error can be expressed, as I mentioned before, in terms of the alpha singular values of the function u you try to approximate. Of course, u is not available, so a heuristic approach is to, given an approximation, you will construct a correction of this approximation, a better approximation of the function u, and estimate the truncation error by the singular values of this better approximation of the current approximation. Okay, this is the way we do it. Of course, with this strategy, we have no guarantee of selecting the best nodes, but this is a way to have an adaptivity in the rank. And here I come briefly to the problem of tree adaptation. So of course, it's a combinatorial problem, so we address this with a stochastic approach, okay, using stochastic algorithms. You could have a very crude approach, which is, okay, let's run a stochastic optimization algorithm on the tree, provided some error estimates, for example, based on validation, that drives your stochastic optimization algorithm. At each step, given a tree, you run the learning algorithm I have presented before, you select the optimal ranks based on validation strategy and so on. But this is a very complicated approach. Okay, fine. If you have unlimited computational resources, you can do it in this way, but this is a combinatorial problem that you try to solve here. So the way we do it is that, in fact, we will use a procedure that adapts ranks and trees simultaneously. So we start with a certain tree, an approximation with a low rank, in fact, a rank 1, 1, 1, 1, 1, very coarse approximation, and then we repeat the following steps. First, we enrich the ranks using the strategy I have presented before. We will select a certain collection of ranks to increase. We will learn an approximation in this format. And then we will run a stochastic algorithm to optimize the tree. But this is not a learning task here. Just what we use are standard tools for compression of tensors. We will try to optimize the complexity of the representation of the tensor that we have at the current iteration. Okay? So it doesn't use the data, just the approximation you have. You try to find a tree that decreases the representation complexity of this. If you find a tree that decreases the storage complexity or representation complexity, then you change the tree and you go back to the rank enrichment step. Let me give you two examples here. First, in a supervised learning setting where we consider this composition of functions I have introduced before in the approximation part. So here I compose, for simplicity, always the same bivariate function h, which is given here. So here's a very simple example where the function is polynomial. So by choosing as background spaces polynomial approximation spaces, you should be able to recover this function for any tree. Because by increasing the rank, at some point, you will fill the space, okay? When the ranks are equal to the dimension of the underlying background approximation space, and you should be able to recover this function. But of course, the tree, as we will see, is really crucial here. It has to be close to the structure of the function here. If you choose a tree, for the representation, which is related to the structure of the function, of this compositional function, you have a representation complexity in this tree-based format of the order of 2,000. But if you choose a bad tree with a bad ordering of the variables, the representation complexity will be more than 1 million, 9 million, okay? Which means that if you have no adaptation of your tree and you run your learning algorithm within this tree-based tensor format, you will need a huge amount of data in order to estimate a good approximation in this format. So of course here tree optimization will be crucial. So here I just illustrate the behavior of the algorithm where we start from a priori a very bad tree. We start with a linear tree with an ordering of the variable which is random. Okay? So very far from the structure of the function. And then the algorithm starts, so with this tree, and a rank 1. Well, the approximation, several percent of a relative error and certain complexity. And then it decides, so it enriches the rank and decides to change the tree because this tree gives a lower representation complexity of the current approximation. You decrease a little bit the error, not too much. But along the iteration, the algorithm will enrich the rank, change the tree, compress, enrich the rank, and so on and so on. So if you reinterpret this in the setting of neural networks, it would be a sparse neural network, but where the architecture is adapted on the fly, okay? Based on some truncation steps, selection of a new architecture because it gives lower representation complexity, and so on and so on. Well, and at the end, he has found the structure of the function, and then it doesn't change the function anymore, so the optimization step of the tree never find a better tree, so it just enriches the rank. And you see here, up to an accuracy, which is almost a machine precision. So you have recovery of the function here. The sample size initially was, okay, quite high, 10 to the power 5. And here you have a table where you use different number of samples. The training size is from 1,000 to 100,000. And you see that here what is indicated is the probability that the algorithm at the end recovers the structure of the function, the optimal tree. With such an amount of data, we have a very high rate of success, a lower rate of success with less data, but it's not too bad. You obtain very accurate approximations, even with a small training size. And last example is on density estimation. So here I consider a truncated multinormal distribution. So this is the density function that we would like to recover, and we will use a L2 density estimation setting. The approximation spaces on the leaves will be considered as polynomial approximation spaces, but we will adapt the degree, okay? So the procedure will be adapted with the technique working set strategy I had presented in this in the learning part. We will choose here a particular covariance function which is like this, and after a permutation you can see a block structure in this, which means that in fact the density has this particular structure as a product of functions of groups of variables, okay? So this is a particular graphical model that we have here, and the ranks of the different functions here are rather low. Okay, but of course, rather low, sorry. The rank of one of the two functions is 1, and so on. You can have some ideas about the rank of this function for this particular node. So the ranks being low for this particular node, we would like to have a tree containing these nodes, okay? But we don't know a priori the structure of the function. So we run the algorithm, and with different number of samples from the distribution. So for a low number of samples, 100 samples, clearly it's not sufficient to estimate the density. You find a tree which is far from the optimal we have discussed before. But when you increase the number of samples, you can see a nice decay of the L2 error. So maybe it's, and at the end, when you have a large number of samples, you can see that you find a tree containing the nodes I had mentioned before that respect the structure of the graphical model. And what is nice when you look at the L2 error, that you find a convergence rate which is in 1 over square root of n. No dimension here. And this is in fact the minimax rate for analytic densities. These are results that exist in the literature. So it's quite nice that, okay, we use polynomial approximation spaces and we recover the best we can expect in a learning setting with this adaptive algorithm. And last comment I have mentioned, of course, the complete learning theory and the result I have mentioned requires to have a minimizer of the empirical risk. I have proposed heuristic strategy, but there is no guarantee that it is in fact the minimizer of the empirical risk, what we have obtained. So there is a lot to do on algorithms, like algorithm presented by Wolfgang, to really obtain algorithms that converge to almost the optimal approximation, minimizer of the empirical risk. And more importantly, I would say we should follow the road of Wolfgang and introduce really approximation classes for tensor formats and try to divide black box algorithms that achieve almost an ideal performance for these approximation classes. But these approximation classes for tensor formats as neural networks are not well understood. Okay? They are clearly not standard regularity classes. So there is also a lot to do in order to better understand what are the approximation classes for these formats. Thank you.